Alright, now it's time to talk about oxidation reduction reactions, or as the cool kids like to say, redox reactions. So the types of reactions that you're probably familiar with are single replacement, double replacement, synthesis, decomposition, and combustion. A redox reaction is not in addition to those five, so it's not the sixth type of reaction. Rather, a redox reaction is just something that these fit into. So all of those reactions can either be redox or non-redox. So it's actually a category that we look at an individual reaction and decide, is it redox or is it not redox? So what a redox reaction is a transfer of electrons. It's all about electrons. So if one substance loses electrons, another substance gains those electrons, it's called oxidation reduction. The substance that loses electrons is oxidized. The substance that gains electrons is reduced. So that's where the oxidation reduction comes in. And these two have to go hand in hand. You can't have oxidation without reduction, because in order for something to lose electrons, it has to have something to give the electrons to. Just like reduction can't happen, you can't just have a substance that absorbs an electron without getting it from someone else. So here's an example, a piece of iron that's immersed in a copper sulfate solution. You'll notice that sulfate is nowhere in this equation. It's because sulfate's a spectator, it's soluble. But what's happening is iron, if we look at iron, it went from a solid, no charge, so neutral, into a 2+ charge. So if something becomes positive or negative for that matter, that means it's losing or gaining electrons. So if it became 2+, that means it lost 2 electrons. So it lost 2 electrons in order to become Fe2+. Now copper was Cu2+, and then it turned neutral, it turned into a solid, which means that it gained 2 electrons. And that's called reduction. Oxidation is loss, reduction is the gain. And so then what happened in this reaction is iron transferred its 2 electrons over to copper, making it Fe2+ and copper neutral. So calcium reacted with oxygen to form calcium oxide. This is actually another redox reaction, but we can't look at the charges on this one and see, okay, who went from positive to neutral and who went from neutral to positive. Instead, we have to do something else called oxidation numbers. And there's several rules for assigning oxidation numbers, and really it's just about practice and kind of learning and getting familiar with these rules. And the way this looks is we write numbers above the different elements or in the reaction, and then we can look at how they change. So like calcium in this case is 0, oxygen is 0. Then if we come over to this side, oxygen becomes 2- and calcium becomes 2+. And so what we can see now is that calcium went from 0 to 2+, oxygen went from 0 to 2-. So obviously there was a change of electrons in there. Rule number 1 for oxidation numbers: an atom in its elemental form, its oxidation number is going to be 0. So magnesium and iron, both completely by themselves, not bonded to anything, their oxidation number would be 0. Hydrogen, even though it's H2, it's still just bonded to itself, so it's still in its elemental form, would be 0. O2 would be 0, Cl2 would be 0, and O3 would be 0. So anytime you see an element not bonded to anything different, that means its oxidation number is going to be 0. And next one, for monatomic ion, its oxidation number is equal to its charge. So monatomic, you may not be familiar with that. Mono means one, atomic, atom. So an ion that's a single atom, its oxidation number is the same as its charge. So Mg2+, its oxidation number would be 2+. Cl- would be -1. And for this, it's also important that we recognize ionic compounds. So something like sodium chloride, NaCl, the oxidation number, even though we can't see the charge on sodium and we can't see the charge on the chloride, we should know what those charges are. And so then we could say the oxidation number for sodium would be +1, and the oxidation number for chlorine would be -1. So knowing your ionic compounds, what's ionic and what the charges are. Oxygen is easy. 99% of the time, oxygen is going to be -2. So in water, it's -2. In CO2, it's -2. The only exception is in peroxides, which are tricky. So you've got to watch for the name peroxide. A peroxide is a polyatomic ion of oxygen, and so it's O2, 2-. So how do you recognize the difference between O2 as a peroxide and O2 as in like CO2? Well, you've got to look at what it's bonded to. So if it's with a metal like hydrogen, that means that it's going to be a anion, so 2-. Also look at the names, so they'll tell you things like hydrogen peroxide. You recognize that as a peroxide, and if that's ever the case, that means that it is -1 for its oxidation number. Alright, and hydrogen, whenever it's bonded to a nonmetal, its oxidation number is +1. When it's bonded to a metal, though, it would be -1. And you can recognize it as well. If it's up front, it's going to be +1. If it's the second one, then it's going to be -1. So the easiest ones are the ones that contain hydrogen and oxygen, because you just use your thinker and you figure out what the other one is. However, if there is no hydrogen and oxygen, and it's not an ionic compound, so you can't look at the charges, you instead have to look at the most electronegative element and then use its charge as the oxidation number. So for example, BF3, it's a covalent compound, so it's not ions, but fluorine is the most electronegative, and so we can use its charge to tell us the oxidation number. So fluorine would be -1. And then, since this is a neutral compound, since there's 3 -1s, that means that boron would have to be what? Yeah, +3. Same thing down here, so chlorine is the most electronegative. We would use its charge, and its charge is -1, and there's 5 of those. That means that phosphorus would be +5. And this is just saying what we talked about before. The sum of the oxidation numbers for a neutral atom has to be 0. So since we've got oxygen, which is always 2-, and we have hydrogen, each one is +1. So we write the numbers above. We write the number for just one of them. And there's 2 of them, so that would be +2 -2. That equals to 0, which matches the charge of the atom or molecule. However, not all molecules are neutral. So if we have chlorate, which is ClO3-, we would have to sum up its oxidation numbers, and it should equal -1 in the end. So let's try and do this together. Oxygen is always -2, and there's 3 of them, so that's a total of -6. And then chlorine, if we want to make this equal to -1, that means that chlorine's oxidation number plus -6 should equal the charge of the molecule, which is -1. So what number plus -6 would equal -1? It would be +5. So that means the oxidation number for this chlorine is +5. So let's do a couple practice problems. Let's do sulfate and then NO3, and that's not nitrate, so it's NO3, the neutral version. Go ahead, pause the video, and see if you can give oxidation numbers to all of the atoms in these molecules. So oxygen is always -2, and if we have 4 of those, that would make it -8 total for oxygens. If we want it to equal to 2-, so -2, and we have -8 already, then what number plus -8? It would have to be +6. And then with NO3, oxygen is always 2-, and so that would be a total of -6. So that means that nitrogen would have to be +6 to equal the neutral charge. Alright, so let's go back to our original slide and take a look at calcium and oxygen. So now you should be able to look at these and see why I put those numbers above them. Calcium, that's elemental form by itself, so it'd be 0. Oxygen, elemental form by itself, 0. If we come over to this side, oxygen is always 2-, and calcium then would have to be 2+ since it's neutral. So the next question is, who was oxidized and who was reduced? Here is how you can always remember oxidation and reduction. Oil rig. So what oil rig stands for is that oxidation is loss, reduction is gain. Once again, oxidation is loss, reduction is gain, and it's all about the electrons. So anything that is oxidized is losing electrons, anything that is reduction is gaining electrons. So in order for calcium to go from 0 to 2+, what would it have to do? It would have to lose 2 electrons. And in order for oxygen to go from 0 to 2-, it would have to gain 2 electrons. So what that tells us then is that calcium was oxidized and oxygen was reduced. Alright, here is a full-blown reaction. Let's go ahead and try and first assign oxidation numbers to this. That way we can tell who is oxidized and who is reduced. So pause the video, give that a shot, resume it when you think you got them. Alright, so here is our oxidation numbers. Couple struggles you might have run into, so recognizing that this right here is nitrite, which is NO2- and hydrogen plus. This right here is chlorate, so that means the overall charge of this guy is -1, which means that potassium, It's going to be an ion, and it's going to have a charge of +1, or an oxidation number of +1. And then from there, it's just making sure that these all add up to neutral, since they're neutral molecules overall. So next question is, who is oxidized and who is reduced? If we look at something like potassium, potassium started out at +1 and wound up at +1. So its oxidation number did not change. Therefore, it was neither oxidized nor reduced. So there is going to be things in the reaction that don't change, and that's okay. That means they're not oxidized or reduced. We want to look specifically at the elements that are oxidized and reduced, though. So what numbers changed? Well, we can see that chlorine went from +5 to -1. We can also see that nitrogen went from 3+ to 2-. Now we've got to think about charges. So this is tricky because electrons, remember, they carry a negative charge. So even though you gain electrons, it's going to reduce the oxidation number. So for example, chlorine went from +5 to -1. That means it gained electrons, and it actually gained 6 electrons. And nitrogen, on the other hand, it increased its number, so it went from 3 to +. So it's hard to think about it, but it's actually losing electrons because it's losing negatives. So it lost 2 electrons. So then who is oxidized and who is reduced? Oil rig. So oxidation is loss, so that means that nitrogen was oxidized, and chlorine reduction is gain, so it reduced. So now we can do what's called a half reaction. And so what a half reaction shows is either just the reduction half or just the oxidation half of the reaction. So in the case of the reaction that we looked at in the previous slide, chlorine was reduced. And so if we write the reduction half reaction, we would show potassium chlorate gaining 6 electrons and becoming potassium chloride. Now keep in mind, it's not potassium chlorate that is being reduced, it is just the chlorine, but those other guys are attached to it, so we put it in the half reaction as well. However, since potassium is a spectator, it's not changing, we could also write this reaction as ClO3, which is just chlorate, gaining 6 electrons, and it's forming Cl-. And we can leave potassium out of there because remember, this is probably taking place in a solution, so it's aqueous, so it's not really potassium chlorate. It's potassium doing its own thing, chlorate doing its own thing. And of course we can do it with the other half of the reaction, the oxidation half. So nitrogen went from +3 to +5, so it was oxidized. So if we wrote just the oxidation half, we would show HNO2 turning into HNO3. And notice how if we think about just one nitrogen, a single nitrogen would gain 2 electrons. But with the balancing, there was 3 nitrogens, which means each of those would gain 2 for a total of 6 electrons being lost by the nitrogen. And once again, if we wanted to throw spectators out of this guy, it would be NO2- turning into NO3-, and if we balanced it, it'd be 3, 3, and it would be losing 6 electrons. And those 6 electrons are what were picked up by the chlorines. Aw, it's your very own oxidation reduction problem. So go ahead and pause the video and give this one a shot all the way through. So go ahead and write the oxidation numbers, identify who is oxidized and reduced, and then write the half reactions for me. So take a deep breath, pause the video, give it a shot. Alright, first the oxidation numbers. Here they are. Check them, compare them with yours. So sulfur lost 6 electrons, oxygen gained 2 electrons. And that then means that sulfur was reduced, oxygen was oxidized. Now on to the half reactions. Write one for reduction, one for oxidation. Alright, so here they are. The oxidation half reaction shows oxygen gaining 6 electrons to become PbO. The reduction half reaction shows sulfur losing 6 electrons when it becomes SO2. It's really important to note then that these two numbers match up because you can't have oxidation without reduction. Sulfur had to lose 6 electrons so that oxygen could gain those 6 electrons. Two terms that I really need to show you guys, and that's reducing agent and oxidizing agent. Now, these can be confusing, so you got to think about them carefully. The way you want to think about this is like a travel agent. Okay, a travel agent, if you hire a travel agent, does he buy tickets and then go travel himself? No, he books travel for someone else. So if you see a travel agent, he would help you to travel. So a reducing agent is not what is reduced, it's what causes someone else to be reduced. So a reducing agent is what causes someone else to lose electrons. So for example, in this question right here, sulfur lost 6 electrons. Well, who caused it to lose 6 electrons? It was oxygen. So oxygen would be the reducing agent in this problem. And then who is oxidized? Well, it was oxygen. And in order for oxygen to be oxidized, someone else had to lose electrons, and so that means that sulfur was the reducing or oxidizing agent. Not because sulfur was oxidized, but because sulfur caused someone else to be oxidized. Quick way to think about it, it's just the opposite. So since sulfur was reduced, it means it's the oxidizing agent. Since oxygen was oxidized, it means it's the reducing agent.